All right, so today we're looking at two additional tests, calling them as a group the comparison test, but really we have the comparison test and we also have the limit comparison test. So this is Keeper 3.5, the comparison test. All right, so the first one we call the comparison test. Basically, you want to try to find a function to compare your function to. Now, that function that you find usually is an easier function, something that we can either use like a geoseries or a p-series or divergence test or something like that, that we can compare it to. And so basically, once we find that function, if that function is convergent, and our function, our original function, is less than the function we're comparing it to, then we can say that our function also converges. If the function that we're comparing it to diverges and our function is greater than the function that we're comparing it to, then we can say that it diverges. So what you want to remember here when you're doing this test is that if your function converges, you want to be less than that. So you want to be less than a converge, but you want to be greater than a diverge. And so visually you can see it in the two graphs that we have here. In the top graph, the red series is the one that we're comparing it to. So if that series converges and our series is less than that, then I'm also converging. Like that series is also converging. However, in the bottom graph, the red graph on the bottom is the series that we're comparing it to. If that diverges and our graph is greater than that, then that graph must also, or that function or that series must also be diverging. All right, so here's an example. We have the series or the sum from n equals 4 to infinity of 2 over n minus 3. I'm looking at this and I'm like, I could do an integral test. The integral test takes a little bit longer because I have to check my conditions. I really don't feel like doing all that. So I'm just going to compare it to a function that I know. So again, you want to kind of compare it to something that's pretty easy. And so for this particular problem, I'm going to compare it to 2 over n. All right, in other words, I'm going to ignore that minus 3 because that minus 3 is not really affecting my life. And so when I compare it to 2 over n, I know the sum from n equals 4 to infinity of 2 over n, I know it diverges for sure by p-series. And the reason I know that is because p equals 1, which is less than or equal to 1. All right, so since n minus 3 is less than n, so now I'm comparing my two functions, and 2 over n minus 3 is greater than 2 over n. Remember, when I change it to a fraction, I have to change the inequality sign. Since the function I started with is greater than the function I'm comparing it to, and the function I compared it to was a divergent function, that means that my series 2 over n minus 3 is diverging as well from the comparison test. Remember, you want to be greater than a diverge. If you're greater than a divergent function, then your function also diverges by the comparison test. All right, so the next one, we have this sum from n equals 0 to infinity of 1 over 3 to the n plus n. Again, I don't even know if I could use the integral test or anything else on this. I'm just going to go straight for a comparison test. And I'm going to compare it to 1 over 3 to the n. And I can rewrite that 1 over 3 to the n to look a little bit more familiar to me, and I can rewrite it as 1 over 3 all to the n. And by rewriting this, I see that now I have the geoseries, and since my geoseries, since the r is less than 1, r being 1/3, I know that this series converges. So basically now I need to show that my function is less than the comparison function because I want to be less than a converge. So I'm going to start with my function of 3 to the n plus n. I know that's greater than 3 to the n. And then I'm going to flip my inequality by making it a fraction. So I have 1 over 3 to the n plus n is less than 1 over 3 to the n. And because of that, remember, you want to be less than a converge. And as long as you're less than a converge, then you know that your sequence is also going to converge by the comparison test. All right, so next we have the limit comparison test, which is very kind of like similar test where you're finding something to compare it to. And so basically what you want to do is you want to find a function to compare it to, and then you want to test the limit of the ratio of the two. So the limit of your original function over your comparison function. And as long as that limit is a positive finite number, then whatever the comparison function is doing, your original function will do the same. So if your comparison function converges, then your original function will also converge. And if your comparison function diverges, then your original function will also diverge. All right, so you have example 3. We want to determine if it converges or diverges. And so this is the same function that we did earlier, or very similar to the one we did earlier. We have the sum from n equals 4 to infinity of n squared over n cubed minus 3. And so my a value, or my a function, is the original function we start with, so n squared over n cubed minus 3. And my b sub n, I'm going to use 1 over n. And the reason I'm going to use 1 over n is because I know if I multiply n times n squared, then I'm going to get n cubed. And n cubed over n cubed, that limit is going to give me a function that, or a number that's finite and positive. And so I'm going to do the limit as n approaches infinity of n squared over n cubed minus 3 over 1 over n. All right, so then when I take that limit, I simplify it out, I get the limit as n approaches infinity of n cubed over n cubed minus 3. That limit equals 1, which is a positive and a finite number. So now, since I know that the sum from n equals 4 to infinity of 1 over n diverges by the p-series test, since p equals 1, which is less than or equal to 1, I know that my function also diverges by the limit comparison test. All right, last example, we're determining if this series converges or diverges. Again, I'm going to start with my a sub n, which is my original function, and I'm going to compare that to or use a b sub n of 1 over n squared. And again, I'm using 1 over n squared because I know n squared times the n in my numerator will give me n cubed, which is the degree of my denominator. And so, again, I'm going to take the limit as n approaches infinity of the ratio of the two functions, a sub n over b sub n. I went ahead and flipped it. And so when I take that limit, I'm going to be left with 2. And 2 is a positive and finite number. So all I have to do is figure out whether b sub n converges or diverges. Well, since b sub n is 1 over n squared, I know that it's going to converge by the p-series test since p is 2, which is greater than 1. And since b sub n converges, a sub n is also going to converge by the limit comparison test.